All right. So thanks a lot for the invitation and the introduction. So yeah, as introduced, so my name is Raghav. And I think I do have like a slightly broad set of research going on, but today I'm going to try and focus on one of the more recent line of research that we've been working on resource efficient machine learning. And I think the topic today perhaps is also a little more topical with some of the recent news of some of these big AI models that have been, making a splash. So I'll be talking about the carbon footprint of deep learning, and maybe we can try and see why this is something that we should pay attention to, and then what are the implications of this. So I think I usually run out of time sometimes, and then I don't get to thank my collaborators. So I start out by, thanking them. So this is all the collaborators that who've been working with me on most of the work that is going to be presented here. So like as introduced, my PhD is actually in medical image analysis, meaning I've been developing a lot of machine learning based methods for automatic analysis of images, both with an implication that, it can accelerate the workflow in hospitals and ease some of the burden. And also, these open up like very interesting computer vision challenges. And I think this has advanced some bit of the machine learning research that I will also be showing as part of the talk today. Because I work with interdisciplinary researchers, that's sort of my teaching responsibilities at the university. So I get to do a lot of interesting applications of machine learning. And some of this actually ties to the direction of using machine learning for environmental sustainability. And then I have like a couple of examples here. For instance, in this paper, we actually used, some of the deep learning methods to characterize the behavior of narwhals in Arctic region using, some of their sensor data. And then we developed a method for unsupervised clustering of insects, from laser data. And this is just to kind of say that there's a lot of value in using machine learning methods as tools to tackle, the climate change that we have. And then there are some very interesting contributions that these tools could make. And I think that's why the current talk, for instance, is very interesting for me, because we also don't want to be in a situation where perhaps these tools, when very widely used, can also have a negative impact on climate. And maybe we will see if you're convinced or not about that, through the process of this talk. So this is sort of an overview of what I'm going to present. Firstly, I'll give like a high-level overview of what the recent trends have been, and then trying to point out these costs, and then present some tools on how you can measure these, and then a couple of small projects that we have going on right now on how you could mitigate and what we are trying to do, and then generally what the community is trying to address. I think this is sort of by now an established fact that, the deep learning revolution is here. So it's not necessarily because of the recent, tools such as ChatGPT, but then also in the past 3 to 4 years, several tasks which we thought were going to be impossible have been solved, both in like, for instance, language translation to protein folding to, computer, vision tasks. And I think all of this is accelerated because of what we call as the big data. And I will give like a quick overview of that. But before that, I love this, image that was generated using before, I think ChatGPT took over. There were, small string of other text to image models where I think some of us at least would have tried playing around, typing in like crazy prompts and then seeing what these models were generating. And this is one of those models. It's called Stable Diffusion. And then Copenhagen notoriously is quite rainy, but then this made it into a very beautiful picture out there. And this model was trained using, 500 million images. And then it requires hundreds of GPU days. So meaning if you had a single GPU to train this model, it would take 100 days, but usually we parallelize it and we end up, scaling down on resources. So I think there's been a lot of impact in different applications. But if you actually look at the methods themselves, they're not very new. Like all the technical tools that are being used in deep learning, they're actually a couple of decades old. Maybe they've been matured a bit, but then the fundamental tricks and then the tools that we use are, from the 80s even, or even earlier than that. So what changed? It's the access to big data and then big compute. So it was not feasible previously to have like 500 million images or a billion images and then train these models, really large models. And it's in the past, I would say, the decade or so that we've had access to easy data storage and then scalable compute. And this this is what has made it possible that all of these deep learning models have matured all of a sudden, or it seems like it, but the tools were there, and it's sort of like this coincidence that now we have tools which are converging with the data and then the compute. So then what happens in deep learning is basically what we call over-parameterization. So meaning we take a model which so usually from a statistical, modeling standpoint, if you have 500 million images, then, so you don't want to have like one parameter per image or something like that. But deep learning actually goes contradictorily. It takes even larger models. So if you have 500 million images, then you want to go into even higher scale. So this is called over-parameterization. So when we want to take these large models on large data sets, it requires large compute. And this is where, we are in this current situation that the amount of compute that is required for deep learning is doubling almost like 3.5 to 6 months. This is actually an estimate made by OpenAI early on in, I think, 2018, 2019. And this trend has actually continued on. And if you know what is this Moore's law, it's like a colloquial term for saying that amount of compute on silicon doubles every 18 months. But if we can stick to Moore's law, this does not actually catch up because we are doubling every 6 months, say. So what deep learning, the way the compute has happened is that we scale it in parallel. Instead of running it on a single chip, then we take like a cluster of these and then do training in parallel. Which means we no longer are running on laptops or a single GPU workstations, but then we train these models and deploy them on big data centers. And we were just talking about this, that actually the information communication and technology sector, it's estimated that the greenhouse gas emissions due to the electricity consumption of these big data centers and all the ICT related to it is about, if you don't do a conservative estimate, it can be even 3.9%, which actually puts it even more than the global aviation sector, which I think is estimated to be around 2.5%. And this is a little tricky to say what portion of this is because of deep learning, but then given the trends, I think, larger share of this data center consumption could be, down the line because of deep learning. So we need to sort of, start paying attention to this. So just to kind of, drive home this point, let's look at something I'm sure most of you have, played around with by now. So ChatGPT is based on a GPT-3 model, which I think was released in 2018, 2019 in that horizon. And it has 175 billion parameters. This is sort of like a back of the envelope calculation. No, actually not back of the envelope, but then we don't have access to the compute to run ChatGPT. So I ran a simpler model and then made some approximations on a single standalone GPU. And according to these estimates, every time you interact with ChatGPT, it costs about 0.2 kilowatt hour, which is like charging your phone about 40 to 50 times. Now, in the first month of this year, there were about 100 million users for ChatGPT, and then about 590 million queries were made. And this amounts to 343 gigawatt hours. So for the same month, if you look at it, it's like 250,000 Danish people's, energy consumption. So, which is, of course, it's a big number. And why is this? And I think this is basically the stage that we are, because ChatGPT is the most popular of these AI ML models. And the energy consumption is non-trivial. So if this is the extent that it is, taking up, so we need to pay attention to it. And then otherwise, this is going to create some bit of like I said, negative climate impact if we want to use this to solve climate change, for instance, or make it as a tool to facilitate that. So just to clarify here, I'm not saying that deep learning is a significant contributor right now, but given the trends and then given the widespread adoption that is happening, it could soon become that. And I think as the researchers, this is one of the points that, okay, maybe we should start early instead of looking at it once it's too late, perhaps. So that's where we are at right now. And then here is where we are trying to make some interventions and then try and see what is happening. So the research focus of my team currently is to improve the environmental sustainability of ML at every step, because deep learning model lifecycle is quite elaborate. So as we looked at it, like the first step is like you want to curate these really large data sets, and then the space from which you can choose these models is also quite massive, just because you have 175 billion parameters, and then there's different hyperparameters as we call them. So you have very many recipes to follow to make these deep learning models. And once you have arrived at that model, then the training is expensive. And then how do you make it efficient so that you can run it on your phone, and then model development. So at every stage, we have some projects trying to investigate how can we make them more energy efficient. So in this talk, I won't be talking too much about all of the projects, of course. So I'm going to maybe pay attention to how we can choose models which are inherently efficient. But before we get there, so we want to improve something, but you want to be able to first measure. And I think right now, it's not so easy or straightforward to say what is sort of the carbon footprint of all of machine learning, because it's not a very common thing to report them. So keeping this in mind, there are some tools which are out there which can be used to estimate the carbon footprint of developing and deploying deep learning models. So I'm going to just quickly enumerate. Those of you who are interested, you can go and then take a look at these tools. So the first one is called ML Emissions Calculator. It's a self-reporting tool that you can go and then type in your parameters saying like, hey, okay, I'm based in Denmark, and then I trained my model for 8 hours on this GPU. So what is my energy consumption? So this is sort of a self-reporting way of doing it, and it generates a nice report. And then the other three are sort of tools which can track the energy consumption while the model development is happening. So all the tools except the ML what is the first one, the ML Emissions Calculator, they measure the dynamic RAM costs, CPU and GPU costs. These would be the key contributors when we look at the energy consumption of training deep learning models. Of course, it excludes a lot of other networking overhead and things like that, but we usually account for that with a small penalty, what is called as the power usage effectiveness. And yeah, so depending on what use cases you are, you can track or predict or report. So here, sort of one of the tools that we put out was Carbon Tracker early in 2020. And I'm gonna, because it's something that we know how it works and things like that, I'm going to try and give you like a quick overview. And if you've used Python, and then if you're interested in using this, it's a simple tool. You can install it with a single line of code, pip install Carbon Tracker, and then there you go, you have it. And it's easy to use and all that. It's been, I think by now, the package has been downloaded 67,000 times. So which means there's some interest in the community, at least, to try and look at this. So what happens, I will not get into this, but then it's a simple interface. You have to include like 4 or 5 lines of code. Once you do this, this is what the output of the code would be. So it predicts the energy consumption for the task that you have scheduled. And then if you run the whole task, then it also measures what is the energy, time, and then the CO2 equivalent. And if it's in Denmark or in the UK, we can actually fetch the live carbon intensity from the power grid. So it can measure the instantaneous carbon intensity and then use that to measure the carbon footprint. And in the end, if you tell somebody that, okay, your carbon footprint is like, 10 kilograms CO2, it's a little abstract. So what we do is finally we report it as, if you were to drive a car, what would be the, how far would you go with the same carbon footprint? This is just for an example here, but then the GPT-3 model that I mentioned, the training of that model actually cost the same carbon footprint as if you took a car that is registered in the EU and then drove about 700,000 kilometers. So that's like, I don't know, 30 times around the Earth or something to that effect. So it's quite massive. So given that now we have these tools, to measure, what can we do? So I think I'm going to talk quickly about some of the current research that we are doing in, how we can, for instance, like I said, in model selection, how can we select efficient, neural network architectures? So the simple idea is that, so every time deep learning models are optimized or trained, we have a certain objective which we optimize, that we want it to be good at a specific task. And this task could be in image classification, saying if it's an apple or an orange or a car or a cat or a dog. So that's one task. Or if it's a language model, you want it to be good at translation. Or if it's a self-driving car, you of course want it to be very good at, guiding you in when you're driving. So you don't want any mistakes. So you're of course optimizing for these performance metrics, as we say. So a simple experiment we did was, instead of just using these performance metrics, should we include the carbon footprint also in trying to optimize? Meaning, can you give us a certain performance while keeping the carbon footprint, small? So what would happen to the space of architectures and things? The specifics of this does not, does not matter. But then this is for like an image segmentation task for, segmenting chest, lung masks, and then you want this vertical axis to be as high, meaning you're getting sub-pixel accuracy, from these models. And on the horizontal axis, you have the, CO2 equivalent, or the distance that you would travel in a car. And these different markers are corresponding to different model complexities. So it starts from 100,000 parameters, trainable parameters, to 30 million parameters. So it's just exploring a space of, models in this setting. So of course, the general intuition is that if you have more parameters, you would end up taking more energy, and they also would do better. And that seems to be true for us. So here, the triangle one is 30 million, and then there's another which is about 17 million. So these two models do almost the same, but then they take also a large, the carbon footprint of these models is also quite large. But what if we only had a certain budget? So if you say that, okay, give me the best model, which only consumes 100 grams CO2, these really big models suffer. So their performance drops quite a bit. And then all of a sudden, these smaller models become more appealing for us. So this was a very simple, constraint to pose, saying like, okay, if you also look at, the drop in performance, it's relatively small. And for this task, maybe it does not make that big a difference. But then maybe if it's another task, it would be very important that you actually get to this, from 0.76 to 0.764. But if you're not that sensitive, for instance, if it's a language translation, and if it's just one word or a few characters which go here and there wrong, then perhaps it's okay if you can drop the energy consumption. So this is sort of just opening a new way of solving these model selection tasks. And we took this further into what we call neural architecture search. So this is a space, it's a discrete optimization task where you explore the space of neural architecture so that you can find the best model. It's an optimization, but then not of the parameters of the model, but the models themselves. So given like, a large space of neural networks, can we access the ones which are most efficient? Let me just quickly illustrate here. So each dot here is actually a neural network, and which has a certain performance and then energy consumption. So there's a bit of a cropping here, but then this is energy on this axis, and then performance. Of course, you want the performance to be, very good. And if you only look at the performance as a metric, like with the previous case, you end up somewhere around here, because these are the models which do really well, but they also incur a lot of energy costs. But what we are proposing in this case is that we would like to access this subspace where the drop in performance is actually not, that significant, but the drop in energy consumption is quite drastic. So how do we then explore this subset of architectures instead of always going and exploring these? This is our current work where we are trying to do this using what we call a tabular benchmark. We are making like a data set available so that researchers can explore this as a discrete optimization task. And as soon as we made this data set, we started seeing like, okay, what happens, when you, why is it that this model is so expensive and this is not? So this space has about 400,000 architectures. And this is just to say that if you take some operations in a neural network, so those of you who've used neural networks, you might know that there are, these convolution operations, and then you can have a kernel of size 3 by 3, or you can reduce the kernel size to 1 by 1, and proportionally that would reduce the number of parameters. And if you were to switch, so this is the old operation to new operation, if you switch a convolution 3 by 3 to convolution 1 by 1, then the training time actually reduces by 25%. The energy consumption goes down by 20% with only a drop of 0.03, in accuracy. Now, again, for your task, is this drop critical or not is up to the practitioners. So this is how the space is sort of, perturbing. So you can switch different operators and then see what is happening and then what is happening to your performance. You get like a different configuration of a neural net when you do this. Now, how do you then use this? So instead of using single objective optimization, saying that, okay, only improve my performance, can you also include, energy consumption? And then we do this in what is called multi-objective optimization. So where you optimize both energy and the performance, and then you look for models which you can have like a good trade-off. So this knee point is where you have a good trade-off. You get like very good performance on this axis with very limited, energy consumption. If you did not pose any energy consumption constraint, then you would get this model, which has really high energy consumption, also has a very good performance. But we want to explore this space. And this is a simple sort of a multi-objective setting where instead of just looking for, hey, maximize, or in this case, minimize my performance, negative of the performance, just maximize that along with my energy consumption should be as small as possible. So what happens to this space of solutions? Let me just go to this plot here. So here, these are the green, the yellow, and then the blue points. So the blue point here, this is a radar plot, which has 4 axes. On one axis, you have the performance. You want it to be as high as possible. On the other axis, you have the training time of this model, the energy consumption, and then the number of parameters. So the blue model has a large footprint on all, including performance. It takes a long time to train. It has very many parameters, and its energy consumption is also quite high. But if you explore this space and then you end up with, the model at this knee point, that is the yellow one, there's no significant drop in performance, but it reduces all the other axes. And this is what we want to encourage, like as practitioners, like if we just immediately pose this additional constraint, you don't drop a lot of performance, but then you can immediately get access to these very interesting architectures. Now, this is sort of like, ongoing work. And then we've demonstrated sort of saying, okay, there's not a lot of performance drop when you do this. But as a, general practitioner, perhaps, who does not have so many, such interest in technicalities, what can you do? You can still do small changes if you're developing your deep learning models. We put this out as what we call the theta guidelines. So the first step is that for transparency and then to encourage discussion, we should track, log, and report all of the carbon footprint and then the energy consumption, because this is the first step that the community then stops and pays attention to, saying like, okay, wow, if every time I type into ChatGPT, this is what the energy cost is, then perhaps, we're going to start thinking about how we can reduce it. But if we are not aware of it, so I think as I would encourage, those of you who train deep learning models and then report them, to use some of the tools that I presented to track and log and report. And when you choose hyperparameters, like when you select the space of architectures, we can do something smarter than doing a grid search, as we would call. Instead of enumerating all possible scenarios, you can do a Bayesian optimization or a random search or something like that. We can also switch to energy efficient hardware. So for instance, there are some settings on local hardware which can be introduced to make it more efficient to train. And then what is called as PUE. PUE is the power usage effectiveness. So in a data center, for instance, for every watt of compute, sometimes there's almost a watt of cooling cost. So you want to then choose the right data centers which are highly optimized. So if you have an opportunity to do that, you should also look at. And some very strange things like training location and time are important, is what I've said there, because the carbon footprint during the day in your power grid also is fluctuating quite a bit. So Denmark is famous for having a lot of wind energy and other renewables. But during peak hours, just the wind energy is not able to meet all the demands. So then there's more coal power. So then the carbon footprint of the power at that point increases. So if you are able to, and this data is mostly public in several countries, and then if you're able to monitor that, you want to move your job, training, etc., during the low carbon, intensity times, and training location as well. So if you're using a cloud instance, sometimes you have the opportunity to choose the locations, and you may want to optimize that to minimize your carbon footprint. And these are sometimes problematic in how they would turn out, but these are some things we can start thinking about. And in machine learning, in deep learning training, you can also do something called as automatic mix precision, or doing things in lower precision instead of always doing in 32-bit precision. This also gives us some interesting trade-offs. And also, like, just a high level, publishing pre-trained models and pre-trained data so that not everybody has to redo the whole thing is a good idea, so that we're not wasting compute on just recomputing stuff that has already happened. So I think there are some behavioral changes and some algorithmic things here, but I think these are some initial suggestions as to how we can, after having identified the carbon footprint of deep learning models, how we can try and improve a bit upon these. So, yeah, I think sort of to give like a high level, the thesis of the work that we are doing. So this is also why I think it's important to look at the sustainability of machine learning, because the technology can never be, decoupled from its material costs. And it's sort of when we start talking about how deep learning can be used, or AI can solve the climate crisis, for instance, that it can be a very effective tool. It could be, but we should also be careful in ensuring that it doesn't become a problem in itself. So, and I think paying attention to that is an important point. I hope that's sort of what I'm trying to make with my talk. And that I think I've established with how there's really massive resources that are required currently to develop deep learning models. And if you look at publications in computer science, so mostly we compare models by how fast they are, and then this can be a little misleading, because like I initially said, instead of training it on one GPU for 100 days, you can train it on 10 GPUs for 10 days or 100 GPUs for 1 day. So it's not an equal measure. So I think we want to, that is why carbon or energy are more equal as resources if we like to compare. And from a research point of view, having these resource constraints also like really opens up very interesting, topics of research where, for instance, the mass work that I showed, or there's very interesting work on model compression and then dataset condensation, as we call it. So this is also kind of introducing additional ways of solving these problems, because I think a lot of the progress in deep learning has happened because we did not think about these constraints. But I think now we are at a mature state where we can start posing these constraints and then stop doing this brute forcing over large data using large models. And that being said, it's not straightforward to quantify the carbon and energy costs. For instance, it doesn't at all take the hardware manufacturing into account. And yeah, because the supply chain is so opaque, and then how do we do that? But I think viewing the algorithmic efficiency is like the first step towards maybe getting there. And there's also the aspect of de-democratization of AI. I think this is something that also bothers me as a researcher, because some of the really new big AI models at the University of Copenhagen or in other universities in Europe, we don't have the compute resources to reproduce those or replicate those results. And this is a bit of a problem, because if this is the case in the global north, this is going to further percolate in the global south, for instance. And then if we want to have like these models to be used in policies and in climate action and things like that, we also want it to be democratically developed, than just saying like a few key actors are going to develop and then we're all going to use them. And I always have like this sort of existential question about my own research, saying that saying that AI will solve climate action is like one techno-solutionism, and then I'm saying like we can use another layer of technology on making them more efficient to solve this. So it's like this cascaded techno-solutionism. But I think it's good to have like that doubt myself then. So it poses some interesting questions, I think. And just to plug Carbon Tracker again, so just try it out, and then if you have any problems, just raise GitHub issues or write to me. So that's my current team, and then you can reach out, and some of the work that I presented here is funded by the EU on these two grants. So I'm open for discussions now.